Hello students. So today we are going to write a program to check whether given number is prime or not. The number has to be taken from the user and then we need to check whether the number is prime or not and display it on the console. A number is said to be prime if it does not have any factor other than 1 and itself. So to check whether a given number is prime or not, what we can do is we can start with 2 and check whether 2 is a factor of the given number. If it is, then we can say that the number is not prime. If it is not, then we can check whether 3 is factor of the number. If it is, again we can say that it is not prime. Otherwise we can check with 4, so on and so forth up to n minus 1. We can check whether we find any number which is factor of the given number, and if we can find any number, then the number is which is factor of the number, then the number is not prime. Otherwise, if none of the numbers between 2 to n minus 1 is factor of the number, then the number is prime. So whether it is absolutely necessary to check up to n minus 1 um, that there is any factor between 2 to n minus 1 of the number or not? The answer is no. We can do better by a huge margin by checking just up to floor of root of n. So why am I saying so? That we can see by an example that for any non-prime number other than 1 and itself, all the distinct factors lies between 2 to floor of root of that number. So I will take an example and show you that this is indeed the case, that all the distinct factors of a non-prime numbers lies between 2 to floor of root of n. 2 to floor of root of n. What is this floor operator? Floor operator is floor of a number is greatest among all the numbers which are lesser than the number. Greatest among all the integers which are lesser than or equals to the number. So if we have 3.3, floor of 3.3 is greatest among all the integers lesser than equals to 3.3. So the integers lesser than equals to 3.3 is 3, 2, 1, 0, minus 1, and all integers, all negative integers. So among this, 3 is the greatest integer. So 3 is floor of 3.3, and similarly floor of 4.2 is 4, which is greatest among all the integers lesser than or equals to 4.2. So um, our statement is that all the distinct factors of a non-prime number lies between 2 to floor of root of n. We can take an example and see for ourselves that it is indeed true. So let us say that the number is 36. Now apart from 1 and 36, all the distinct factors of 36 lie between 2 to floor of root of 36. Floor of root of 36, root of 36 is 6 and floor of 6 is 6. So that is our statement, that all the distinct factors between of 36 lies between 2 to 6, where 6 is floor of root of 36. So let us take the factors of 36 one by one. So we'll leave 1 and 36. Apart from that, we would start from 2. So 2 into 18 is 36, right? So 2 and 18 are two factors of 36. So I would write all the distinct factors we have encountered till now. So we have encountered 2 and 18, which are two distinct factors of 36. Now 3 into 12, 3 and 12 are 3 into 12 is 36. 3 and 12 are factors of 36. So these are two more distinct factors of 36. Now 4 into 9 is 36. So we have got two more distinct factors of 36, 4 and 9. Now 5 is not a factor of 36. So this is gone. Now what about 6? 6 into 6 is 36. So here we have got 6, which is factor of 36. Now beyond this, so I said that if we can check up to floor of root of n, then we would get all the distinct factors that are there for any number. So these are the distinct factors of 36. Now if we go beyond 6, so 7 is not a factor of 36. We can say 8. 8 is a factor of 36. No, it is also not a factor of 36. We can check with 9. So 9 into 4 is again 36. Now as you can see that 9 and 4 are already included in this list, right? If we go beyond this, then we would get 12 into 3 is 36. Now again 12 and 3 are already included in the list. Now if we go beyond this, we would get 18 into 2 is 36, which are already included in the list. So this way we can see that beyond root of floor of root of n, the factors are getting repeated. So indeed all the distinct factors of a number n lies between, if the number is non-prime, then the factors would lie between 2 to floor of root of n. So we just need to check up to floor of root of n instead of up to n minus 1. So this would improve our algorithm by a huge margin. Now I would write down the algorithm to check whether a given number is prime or not. So we need to start with 2 and see whether it is a factor of the number. Then if it is not, then we can check with 3, so on and so forth up to floor of root of n. So our algorithm would look like this. For we take a loop variable starting from 2 up to floor of root of n. If any of these numbers so if n mod I would first take the value of 2 and then 3, then 4, like that up to floor of root of n. If any of these i's is a factor of n, then n modulo I would return a 0. And if this condition is satisfied, we have got a factor of n which lies between 2 to floor of root of n, and the number is not prime. So we can just print that the number is not prime. Prime. And one more thing that we would do is we would set a flag. We would initialize the flag is prime, say is prime, which would be initialized with true. And when we get a factor of the number, then we can just set this flag to false. And why we are doing that, it would be clear in a moment. And now as we have got a factor of the number and we know that the number is non-prime, then we didn't have to go further to find any other factor. We can just break out of this loop. So it used the break statement to break out of the loop. Now after reaching here, after reaching at this point, we can reach at this point by two ways, either by executing this loop up to floor of root of n in which case that we have not find out any factor between 2 to root of n, or by executing this break statement. So we can reach here in two ways. Either we have executed all the iterations of for loop, or we have executed this break statement. So the case in which we have executed this break statement would have this is prime flags value set to false. So that we need to check. If is prime's value is false, that means the number is non-prime, right? So in that case we cannot just print here that the number is prime. We'll have to check if is prime is equals to true. So if is prime is false, we have already printed out that is it is non-prime, and if it is still true, we can print that it is prime. I hope this requirement of checking this flag is clear. Had we not given this condition, even if the number is firstly printed as non-prime, after this loop, as we would have put this unconditional print statement, it would have again printed that the number is prime. So this print statement has to be within a condition, and the condition is prime is equals to true. Is prime would remain true only if this condition is not satisfied by any of the i's between any of the numbers between 2 to floor of root of n. So this is our algorithm. Now we need to code this algorithm. So it go for coding. So it start with a flag is flag, and we set it to true. So any number which is non-zero in C is considered to be true. So it set it to true, and then we declare a number, an integer, in which we would collect the entry from the user. So we prompt the user to enter a number, and then using scanf statement we get the user entry and store it in the num variable. Now we write a for loop. I'll declare a loop variable first, I, and then we would initialize I with 2, and the stopping condition would be I less than equals to square root of n. So sqrt is a inbuilt library function. Now here inside the loop we'll have to check whether I is a factor of the given number. If I is factor of the number, then it would the remainder, the modulo operation would return 0, and if it returns 0, we would just print that it is non-prime. The number is non-prime, and would set the flag to false. Is prime is equals to is flag. Let me call it as is prime. Better. Would be set to 0, which signifies that we have found that the number is non-prime. And then because we have already found that the number is non-prime, we have got a factor of this number. No need to check any further factors of the number. We can just break out of this loop. Now after coming at this point, we'll have to display conditionally that the number is prime, and the condition is if is prime flag is still true, which is the initial value of is prime flag. So we have initialized so we write 1. So we have initialized is prime flag with 1, and if this condition is never satisfied, is prime flag would never be set to 0, it would remain 1, right? So at this point, if we check is prime equals to 1, it is equivalent of saying that we have not found any factor of the number. So if we have not found any factor between 2 to root of n of the number, then the number is prime. So we can print here that the number is prime. We put a get over here. So we are done with our coding. Now we can build it and run it, and we can check. So there is some problem over here. So yeah, so sqrt is a library function and which is available by including the library math.h. So math.h contains several mathematical functions like this. Let us build it once more. There is some other problem over here. I equals to 2, I less than equals to square root of num. Well, hopefully this time it would build. Yeah, so this time the build is successful. Now let us run it, and let me give 45, so the number is non-prime. Then let me check with a positive case. 19, the number is prime. So our program is running correctly, and this is the code for it. So I hope this is very clear to you, all the code and the algorithm that we wrote, and the reason why we need to check just only up to square root of number. So I hope that is clear. I tried to check it with 9 as well, and let me see if it's working correctly. So the number is non-prime, so it is working. So this code is perfect. Thank you for watching.